his first tape of this set, Professor James K. Mitchell presented an overview of the methods currently available to improve soils in situ and reviewed selection and design criteria for those methods. In this second tape, he will discuss 3 case histories that illustrate the application of several of these methods to dams. These are the Jebba Hydroelectric Project, Nigeria, Jackson Lake Dam near Jackson Hole, Wyoming, and Mormon Island Auxiliary Dam near Sacramento, California. His discussion will cover the significant issues and lessons learned in each case. Once again, it is my pleasure to present Dr. Jim Mitchell.
Thank you, Frank. In the first video, I described and illustrated situations where some form of ground improvement can be used to assure or improve dam safety. Several different methods were described. The information presented included how they work, soil types and conditions for which they are best suited, the levels of improvement that can be achieved, and some relative costs. Methods for evaluating the post-treatment conditions were listed, and a general approach to design was presented. In this second video, I described 3 illustrative case histories and the lessons that they teach. The cases have been chosen to illustrate the application of different methods. They include descriptions of, first, what was done at the site of a major new dam, second, the replacement of an existing dam following its removal and foundation improvement, and third, a dam where ground improvement was required to improve the seismic stability of the embankment and its foundation. In each case, the primary purposes of the ground improvement were to improve stability and to limit the deformations due to settlement and lateral spreading. In each case, the goal was to prevent cracking of seepage barriers and the loss of freeboard. The first project to be reviewed involved massive densification of loose sand at the site of the Jebba Hydroelectric development on the Niger River, about 200 miles north of Lagos, Nigeria, as shown on the map. Construction of this project was started in March 1979 and completed in the spring of 1983. This dam is 42 meters high above the river bottom. It is founded on clean sand river alluvium that contains no fines and only a small proportion of gravel sizes, as seen in the gradation curves. The highly irregular but unweathered and very hard bedrock surface is as deep as 70 meters below the bottom of the river. The photo shows the very uneven rock topography that continues to large depth in the river valley. The subsurface soil conditions were explored in detail by means of the standard penetration test, the cone penetration test, and dynamic cone penetration testing that was done at the location shown in the plan drawing of the dam area. 3 different dam sections were considered to deal with the underseepage problems associated with the large thickness of clean sand and irregular bedrock conditions. First, an impervious compacted fill cutoff that would extend to bedrock. The dewatering, drawdown, and excavation that would be required for this option were estimated to add 1 to 2 years to the project construction time. Second, a concrete diaphragm cutoff wall extending to rock located beneath the impervious core as shown. And third, a seepage blanket that connects to the impervious core and extends 450 meters upstream. The river sand was heterogeneous, varying locally from loose to medium dense. Relative density values ranged from 30 to 80%. Therefore, densification would be needed for options 2 and 3 to avoid unacceptable differential settlements and cracking of seepage barriers. Differential settlement could be caused by the static loads or by low seismic shaking that could occur in this area. The regions near the abutments, between the cutoff wall and the embankment, and between the dam and blanket were considered especially critical for options 2 and 3. The upstream blanket option was selected instead of the cutoff wall for 3 reasons. First, because of the large depth of alluvium. Second, the very irregular rock profile would make keying the wall difficult. And third, cost and scheduling considerations. The overall plan of the project is shown in the drawing. The main dam and the upstream blanket area are of interest in this presentation. The embankment cross-section design incorporated a system of filters as well as pressure relief wells at the downstream toe to control seepage and hydrostatic pressures. Required factors of safety were 1.65 against sliding of the embankment, 1.25 for the embankment stability under earthquake loading, and greater than 2.0 against liquefaction. The densification requirements for the foundation sands were that the relative density should be greater than 70% in the depth range of 0 to 25 meters, greater than 60% between 25 and 35 meters depth, and greater than 50% for depths exceeding 35 meters. The problem from a ground improvement standpoint, therefore, was to achieve and validate densification of the clean sand to great depth beneath a major flowing river. Selection of a method for treatment to depths of 25 to 30 meters was straightforward. Vibrocompaction had been used successfully to improve the supporting capacity of a highway bridge founded in the same sand a few hundred meters downstream of the dam site. Although the required depth of treatment at the bridge was not nearly so great as at the dam, specialty contractors believed that it should be possible to treat effectively to a depth of 30 meters. The biggest problem was in deciding what to do from 30 meters to the treatment depths of greater than 40 meters that were needed in some areas of the foundation. After reviewing all possible options, it was concluded that deep explosive compaction offered the only practical and economical possibility. At the time of this project, deep soil mixing, compaction grouting, and jet grouting were still in early stages of development. It is likely also that the cost of their implementation would have been prohibitive. The maximum required blasting depth of 45 meters was 2.5 times greater than any prior use of blasting. Thus, it was realized that the needed densification might not be attained by explosive compaction. However, if blasting were carried out, the critical zones would at least have been shaken by an intensity equal to that of any earthquake events that were anticipated. Accordingly, a test program was designed to determine if blasting would be effective for very deep densification. The main objective was to confirm that the desired relative density could be obtained. The test program would also provide information useful in resolving the following issues: the blast hole spacing, the depth of charges, the size of charges, the concentration of charges, the effects of different types of explosives, the minimum coverage requirements, the optimal time intervals between coverages. Because of the cohesionless character of the sand, undisturbed sampling for determination of relative density was not possible. Therefore, the well-known Gibbs-Holtz correlation between SPT N value and relative density was used. However, the CPT was to be used as the primary means for evaluation of relative density rather than the SPT. So it was necessary to convert CPT tip resistance values into equivalent SPT N values. A series of side-by-side SPTs and CPTs was done, and it was found that a cone penetration tip resistance to penetration test N value QC over N of 7.5 was appropriate for this site. The diagram shows very good agreement between SPT and CPT curves compared on this basis. The plan shows the layout of the blasting test section. 3 coverages were used. Individual charges varied from 1 to 5.5 kilograms. Charge spacings varied from 5 to 12 meters, and charges were placed to depths up to 36 meters. The cone resistance versus depth curves shown are typical of the test program results. They indicate that 24 days after blasting, the sand had a penetration resistance less than the initial value. By 90 days after blasting, however, the penetration resistance had increased significantly. In fact, the limit of the equipment capacity was reached for depths greater than 32 meters. Owing to the large depths to be treated, an extensive test program was required also to establish that vibrocompaction could be capable of doing the job. The original plan had been to do all the sand densification work from barges. However, the merits of being able to work in the dry from the ground surface justified building a sand pad from the shore out into the river. Construction of the 5-meter thick sand pad by hydraulic filling meant that penetration for vibrocompaction over large areas would now be necessary to a depth of 30 meters in order to reach the 25 meters depth of treatment below the river bottom that had been specified originally. After much experimentation, it was determined that the required depth could be reached by modification of the water jets along the side of the vibrofloat units. The photograph shows the resulting configuration and jetting pattern. The required densification could then be obtained by using a center-to-center probe spacing of 2.75 meters. Once it had been determined that densification could be obtained using deep blasting and vibrocompaction, it was necessary to determine in more detail the zones requiring treatment. To do this, a 20-meter by 30-meter grid was established beneath the dam footprint, and a 60-meter by 60-meter grid was developed beneath the clay blanket. CPT tests were done at the center of each 20 by 30 meter or 60 by 60 meter section. The measured cone resistance values were converted to equivalent relative densities. Each cone penetration test was considered representative of the alluvium for the 20 by 30 or 60 by 60 area in which it was centered. Contours of equal relative density were drawn at 5-meter depth intervals. A set of relative density contours corresponding to elevation plus 70 meters is shown in the drawing. The need for subsurface compaction was then determined using criteria based on the thickness and lateral extent of zones failing to meet specific relative density values. The figure shows the CPT records in relation to the minimum acceptable cone resistance values. Zones where the measured cone resistance is less than the required value define the elevations where densification is needed. The design requirement was considered satisfied if, after subsurface compaction, the penetration resistance reached or exceeded the specified value over at least 85% of the treatment depth. Deep densification by blasting was completed before the vibrocompaction was started. Blasting was required only beneath the left half of the river bottom in the areas defined by the 5 zones shown in the drawing. The production blasting involved placement of charges ranging up to 30 kilograms in grid patterns at depths below 30 meters. Noble Special Gelatin 80, supplied in 25 millimeter diameter and 200 millimeter long sticks, was used as the explosive. 2 or 3 coverages were used in each blast area, with time intervals of several days between each coverage. The charges were installed using a special vibratory pile driver rig and casing. The driver pipe carried a corrugated plastic pipe to the desired depth. After removal of the driver pipe from the ground, the explosives were lowered to the prescribed depth. The driver pipe and plastic corrugated pipe are shown in the photograph. With this rig, it was possible to install 8 to 15 holes per 10-hour shift for holes to 35 to 45 meters depth. The casing size limited the explosive charge that could be placed within it to 1 kilogram per meter. Thus, a 30-kilogram charge required 3 holes spaced in a triangular array, 3 meters on center, and charge lengths of 10 meters in each casing. The photograph shows the surface response associated with the detonation of the charges in one coverage. Ground surface settlements caused by the blasting were typically in the range of 0.5 to 1 meter, as may be seen in the contour drawing. Settlement was almost immediate, with an average increase of only about 4 millimeters during the day following the detonation. Some comparisons between the pre- and post-blast cone penetration resistances are shown in the figure. Measured and required values of cone resistance are shown as a function of depth. The post-treatment resistances are considered conservative in many cases, as the cone is believed to have followed the path of least resistance, with significant deviations from the vertical being measured in many cases. The average improvement in terms of relative density over the full depth of affected material varied between 5 and 16 percentage points. The overall average increase was 10 percentage points. Over 300,000 cubic meters of sand were densified by blasting at a cost of $7.30 per cubic meter, including the relatively high cost of testing. The deepest production vibrocompaction, to 33 meters depth, was done using electrically powered units drawing 150 to 160 amps at full power and operating at 1800 RPM. Compaction lift intervals were 0.3 meters, with a 15 to 25 second hold at each lift. The overview photo shows two rigs at work along the right bank of the river. The close-up photo shows placement of river sand backfill during the vibrocompaction process. The backfill consumption rate was 0.34 to 0.97 cubic meter per meter of depth. The vibro treatment was very effective in improving the sand, as is evident from the before and after CPT results shown in the figure. Before and after penetration resistances are compared with the penetration resistances corresponding to the specified relative density of 70%. The Jebba Dam project was the second largest vibrocompaction project ever done, with a total length of 310.6 kilometers of treated columns beneath the original river bottom. In addition to the foundation sand densification to prevent differential settlements and cracking of the core and blanket, additional safeguards were implemented against piping due to possible dispersive characteristics of the impervious borrow material. Highly dispersive soils had been encountered in some parts of the borrow areas. These safeguards included surface slush grouting and/or shotcreting at the core rock contact and where jointed abutment rock was encountered. The gradation of the transition filter material was maintained on the fine side of the allowable range. In addition, heavy compaction was mandated for the core, 95% of modified Proctor rather than 95% of standard. Performance of the completed dam was in good agreement with predictions. The figure shows the predicted and measured settlement profiles in the dam and in the foundation for two locations and for the end of construction and full reservoir conditions. The ground improvement for the Jebba Dam represents one of the largest soil treatment projects ever undertaken. It involved densification of virtually all the foundation alluvium beneath the embankment and beneath the blanket to a large depth. Several important lessons and conclusions can be drawn from this project. The large depth to bedrock, the very irregular bedrock surface, and the loose alluvial sand were the major factors in the choice of seepage control and foundation treatment. Cost and scheduling issues influenced the choice of treatment methods. Successful transfer from SPT characterization of the sand during the exploration and design phase to the CPT for design and evaluation of the soil improvement was possible using site-specific correlations. The measured penetration resistance reflects more than simply a relative density. Deposit age, fabric, and in situ stress state were shown to affect the measured values. Local experience was an important factor in guiding the choice of soil treatment method. Test programs are the best way to evaluate the suitability and effectiveness of ground improvement methods. They are also invaluable for optimization of procedures and development of specifications. The definition of zones requiring treatment and the development of reasonable, workable, and enforceable specifications is difficult but necessary. There were not then, nor are there now, rules about how much below the design values is acceptable or how large zones can be that do not meet specifications. New and beyond prior experience situations require innovative solutions and experimentation to see that they will work. Examples at Jebba included explosive compaction and vibrocompaction to unprecedented depths. Jackson Lake Dam was completed in 1916. It is located on the Snake River and lies within the boundaries of Grand Teton National Park. The 847,000 acre-foot reservoir is for irrigation and flood control. The dam consists of a concrete section, a short embankment section to the south, and a 4,500 foot long embankment section to the north, for a total length of 5,500 feet. The low-profile embankment dam extends 49 feet above the river bottom and has a crest width of 200 feet. The north embankment was placed by hydraulic filling methods. It was composed of saturated, loosely compacted, cohesionless material. Dam safety investigations indicated that this embankment was susceptible to liquefaction from moderate shaking from either local or distant earthquakes. This liquefaction was likely to cause sufficient crest slumping that the dam would be overtopped. The foundation beneath the north embankment was unconsolidated fine sand and silt. It too was susceptible to liquefaction with similar consequences to the embankment. The poor foundation soil conditions extended to depths of up to about 100 feet. The site is in a seismically active area. The 1959 Hebgen Lake earthquake in southwestern Montana was a Richter magnitude 7.1, and the 1983 Mount Bora earthquake in central Idaho was magnitude 7.3. The Hebgen earthquake caused failure of the Hebgen Dam on the Madison River near West Yellowstone, Montana. There were extensive ground deformations and a number of landslides around the reservoir shoreline. Settlement and cracking of the dam embankment around the concrete core wall can be seen in the photograph. It was estimated that a local earthquake of magnitude 5.5 would be sufficient to cause liquefaction of both the embankment and foundation, with consequent breaching of the Jackson Lake Dam. The probability of failure was estimated to be 40% within the next 100 years. This corresponds to about 100 times the generally accepted level of risk. Several corrective action options were considered in 1984. These included restriction of the reservoir operating pool, modifications to the existing dam, removal and replacement of the north embankment, densification of the north embankment foundation, modifications to the south embankment if necessary, treatment of the concrete dam foundation to provide stability, modifications to the outlet works, and modifications to the spillway piers. Several alternatives to these corrective actions were also considered, including a replacement dam, dams at new storage sites, and operational changes at Jackson Lake with water-saving measures on project lands. There was extensive public involvement in the evaluation of all the options before selection of the final corrective action. Ultimately, it was decided that the concrete dam and the south embankment would retain their existing alignment. The north embankment was to be shifted upstream to minimize environmental impact to wetlands downstream. This therefore necessitated that the reservoir be drawn down while remedial work to the foundation materials was done and a new embankment was constructed. The seismic stability of the new embankment could be assured by use of appropriate materials and proper roller compaction during placement. Of interest in the present discussion, therefore, is the ground improvement that was done to assure a stable and liquefaction-proof foundation beneath the new north embankment. Conceptually acceptable methods for this ground improvement included excavate and backfill. This suffered the disadvantages of groundwater control problems and uncertain costs. Compaction piles. A test section done in 1981 indicated that they would work. However, they were costly and they were time-consuming. Jet grouting. Deep dynamic compaction was also considered a potentially viable method for densification of the upper 30 to 40 feet of foundation materials. Two concepts were developed for the treatment cross-section beneath the embankment. In the end block configuration, shallow treatment by deep dynamic compaction would be used under the center of the embankment. Deep densification would be done beneath the upstream and downstream toes. In the center block method, the locations of the deep and shallow treatment zones would be reversed. The end block method was ultimately selected, and the limits for treatment were defined as shown in the schematic diagram. In this design, any liquefaction that develops in the loose foundation material below the shallow treated area under the central portion of the embankment of the dam will be contained by deep end blocks. This will prevent an overall shear failure. The end block design also includes a seepage cutoff wall beneath the upstream toe. The overall design was based on the criterion that if the standard penetration test N160 resistance value corrected for depth and for delivered hammer energy and for fines content was less than 20, then treatment was required. Approximately 50% of the ground required treatment on this basis. A post-treatment value of N160 of 20 or more was used as the basis for acceptance of the improvement. The suitability of the design was evaluated using analytical studies that included seepage analysis, static slope stability, dynamic analyses, and settlement analyses. When the project was put out for bid, the pattern of columns was described. However, the contractor could choose a method other than those listed. It was up to the bidder to propose the quality assurance procedures to be used. The bid evaluations gave more weight to technical merit than to cost. Deep soil mixing, or DSM, of Portland cement with the in-situ soil was chosen as the construction method for the deep end blocks. At that time, deep soil mixing had been used extensively and successfully overseas, especially in Japan, Sweden, and the United Kingdom for several purposes. However, it had only been introduced recently into the United States. Nonetheless, it offered several attractive features, including cylindrical columns of known diameter could be constructed. Twin or triple parallel drilling shafts are physically linked, so tangential or overlapping continuity could be maintained between adjacent columns. Continuity between adjacent columns in a row could be assured by re-drilling the last one in a row. And full depth treatment eliminated the need for deep dynamic compaction in areas treated by the deep soil mixing. In addition, the same method could be used for construction of the cutoff wall. The deep soil mixed end block widths were established as 50 feet, extending 20 feet outward from the embankment toes and 30 feet inward towards the center, as shown in the cross-section drawing. The deep dynamic compaction was done in 2 stages during 1986 to 1988. The area to be densified in each stage was divided into several sectors. The deep dynamic compaction grid pattern was based on a 40-foot spacing between impact points, 3 phases of treatment, and ironing of the ground surface following the tertiary treatment. The grid layout was designed so that the impact points of each successive phase were between those of the previous phase. The effect of each impact on the ground below is shown schematically in the sketch. As the greatest practical depth of treatment was desired, heavy weights and large drop heights were used, as may be seen in the table. 30-ton drop weights having a diameter of about 7 feet and cranes capable of 100-foot drop heights are at the practical upper limit of equipment that is presently available. Perimeter drainage trenches were used to facilitate removal of water. The illustration shows the deep dynamic compaction work in progress. Over 400,000 feet of prefabricated vertical wick drains were installed to depths of 20 to 35 feet in locations where the standard penetration testing indicated fine-grained liquefiable materials and where silt layers overlay deeper loose material. Extensive SPT testing was used to assess the effectiveness of the deep dynamic compaction treatment. Significant increases in penetration resistance were measured after each treatment phase as indicated in the table. The test results indicate the greatest increase in penetration resistance was for the gravel and clean sands, followed by silty sands and silts. The overall average increase in penetration resistance was more than 10 blows per foot. The depth of recognizable improvement varied from 20 to 50 feet, with sufficient improvement to mitigate liquefaction risk to a depth of at least 30 feet. The wick drains were considered successful in accelerating the rate of penetration resistance increase. Also, additional SPT testing in the Stage 1 area 4 to 6 months after completion of the deep dynamic compaction indicated higher N values on the average than immediately after treatment. The cost of the deep dynamic compaction was $3.50 per cubic yard for the stage 1 treatment and $4.50 per cubic yard for the stage 2 treatment. Returning now to the deep soil mixing treatment, the design requirements were that the cement-treated soil must have a shear strength of at least 200 psi, or 1,380 kilopascals, and that the columns extend at least 10 feet into the till, or non-liquefiable silt underlying the loose materials. Complete treatment of the 50-foot wide zones was not required. Instead, a hexagonal grid pattern was adopted as shown. The theory was that if the soil within the cells liquefied, lateral flow would be contained and overall shear failure would be prevented. Subsequent analyses have indicated also that the increased stiffness imparted to the overall system would increase the liquefaction resistance of the soil as well. Two 36-inch diameter mixing tools on 36-inch centers, driven by the same electric motor and gearbox, were used. These tools were hollow-stemmed shafts with discontinuous auger flights. Flat beater bars were positioned between the flights. An earth auger head was placed at the bottom of each shaft. The template used for the hexagonal grid pattern of DSM columns can be seen in the photograph. The mixing shafts and augers can also be seen. A 1.25 to 1 water-cement ratio by weight with a flow rate to give 573 pounds of cement per cubic yard was determined necessary to attain the needed strength. More than 200 samples were taken from various depths in the wet columns. About 70 holes were drilled into the hardened columns, and core samples were taken. In general, the core samples gave higher strength than the field wet samples. The strength increased significantly during curing, doubling between 7 and 28 days. Strength doubled again between 28 and 56 days, and increased another 40 to 50% between 56 and 112 days. From the extensive strength testing, it was determined that a 7-day wet sample compressive strength of 125 to 150 psi would give the required fully cured shear strength of 200 psi. This provided a quick and easy way to QA/QC the work. The Jackson Lake Soil Improvement Project is a second good example of how two different methods of ground improvement were used for increasing dam safety. At the Jebba Dam, two dynamic vibratory methods, explosive compaction and vibrocompaction, were used to achieve the needed densification over the full depth range. At Jackson Lake Dam, deep soil mixing was used to reach the required depth of 100 feet, and deep dynamic compaction was used for the upper 30 to 40 feet. The overall configuration incorporated N blocks and deep soil mix cells. The design is built on the concept that it is not necessary to treat all of the potentially liquefiable soil beneath the dam. The key consideration is to design a layout so that if some soil does liquefy, there is still sufficient lateral confinement to support structures above and contain any tendency for lateral spreading. Because the decision was made to lower the reservoir and to remove the Old North embankment, the site was well suited for deep dynamic compaction, which is a very cost-effective method, provided conditions are suitable for its use. Another significant feature of this project was that the bid documents for construction of the two N blocks opened the door for alternative methods. This allowed innovations that might not have been possible otherwise. In this case, the use of deep soil mixing. From this first large-scale introduction of the method in the United States in 1988, deep soil mixing has now become a major technology with broad application for such purposes as support of structures and excavations, and cutoff walls for seepage control and contaminant containment. The third case history that I will describe is the Mormon Island Auxiliary Dam seismic remediation. This dam forms a part of the Folsom Dam and Reservoir Project. This project is located as shown on the American River about 20 miles northeast of Sacramento, California. The plan view shows the major features of this project. The Corps of Engineers built the project during 1948 to 1956. The reservoir stores 1 million acre-feet and has a 14.5-foot freeboard at the gross pool elevation of 446 feet. The reservoir provides water for irrigation, domestic, municipal, industrial, recreational, and power purposes, as well as flood protection for the Sacramento metropolitan area. The project was transferred to the U.S. Bureau of Reclamation for operation and maintenance in May 1956. The Mormon Island Auxiliary Dam crosses the Blue Ravine, an ancient channel of the American River. It is about 1 mile wide at the location of the dam and filled with gravelly alluvium of Pleistocene age. The maximum thickness of channel gravel is about 65 feet. The zoned embankment of the dam consists of a narrow, fine-grained core, transition zones, and shells. It is 4,820 feet long and 165 feet high from the bottom of the core trench to the crest at the maximum section. The crest is 30 feet wide. The shells are constructed of dredged gravel tailings from Blue Ravine that are compacted to a relative density of 65 to 70%. The standard penetration resistance, N160 value, is about 25 blows per foot. The foundation was excavated so that the core is on rock for the full length of the dam. The upstream and downstream shells, on the other hand, rest either on rock or on undisturbed gravel alluvium or on very loose dredged tailings. These tailings were redeposited as a part of gold mining operations in the Blue Ravine during the early 1900s. The portions of the embankment resting on rock or on the undisturbed alluvium are stable. However, the loose dredged material was determined to be susceptible to liquefaction during the design earthquake, with the potential to cause catastrophic failure of the embankment. Accordingly, remediation of the foundation soils beneath this approximately 900-foot-long section of the embankment was mandated. The very significant difference between the undisturbed and redeposited alluvium is indicated by average values of N160 of about 47 in the undisturbed material and as low as 6.5 in the free field beyond the toe, with a maximum of 20 beneath the shells in the loose material. Average values for penetration resistance of the materials beneath different parts of the embankment are shown on the diagram. Owing to the high gravel and cobble content of the foundation material, the Becker penetration test was used for most of the foundation evaluation. This was supplemented by the SPT test wherever possible. The drawing shows locations of the field investigations undertaken prior to ground improvement. The Becker test locations are shown by the open circles in the exploration plan. The liquefiable dredge tailings may be seen to underlie the eastern portion of the embankment from station 446 to 458. The coarse gradation of the tailings was a major factor driving the choice of investigation, remediation, and evaluation methods at this project. The particle size distribution is determined during the exploration phase was 5 to 55% cobbles, 43 to 74% gravel, 1 to 14% sand, and 1 to 7% silt or clay. Some sand and silt pockets were also found within the tailings. From the gradation studies, an average fines content of 5% was assumed for estimating the cyclic strength and liquefaction resistance of the material. The design ground motion, specified as a result of detailed seismic studies, is a peak horizontal acceleration of 0.35 g from a fault rupture at a distance of 9.3 miles. The peak horizontal ground surface velocity is 20 centimeters per second. The duration of shaking greater than 0.05 g is 16 seconds. By the time of this project, new numerical methods for estimating the earthquake-induced dynamic deformations of embankments had become available. The Mormon Island Auxiliary Dam remediation represents one of the first projects where these types of analyses were used to aid in the definition of the locations and extent of treatment. For example, the figure shows the original configuration and deformed shape of the dam following the design earthquake if no ground improvement was used. Dynamic deformation analyses were used to learn the effects of variations in the location, width, depth, and strengths on deformations, poor water pressures, and poor pressure migration associated with an early plan that included foundation treatment zones and berms. After consideration of the results of analyses of this type, the Corps of Engineers and the U.S. Bureau of Reclamation chose deep dynamic compaction as the primary method for ground improvement. Compaction grouting was to be used as a supplementary method if additional improvement was necessary. Ultimately, deep dynamic compaction was used for densification beneath the upstream embankment. However, compaction grouting was not. The upstream and downstream treatments were done as separate phases, with the upstream work done first. Advantage was taken of the very low level of Folsom Reservoir in 1990, owing to the drought in California. Deep dynamic compaction was used based on the available time, the technical feasibility, and cost considerations. A portion of the upstream embankment was cut away, as shown, to enable treatment to the necessary depth and to put the treatment zone as far beneath the upstream toe as possible. Analyses showed that this location is the most favorable for control of dynamic deformations. The berm was incorporated into the design to allow access without having to lower the reservoir, should it be necessary in the future to remediate beneath the zone treated by deep dynamic compaction. The layout for the deep dynamic compaction and the locations for the Becker penetration tests and SPT testing are shown in the drawing. The total treatment length was 800 feet with a width of 150 feet. The target values of post-treatment N160 were a minimum of 23 blows per foot at the surface and 17 blows per foot at a depth of 60 feet. A 35-ton drop weight having a diameter of about 2 meters at its base was used. A drop height of 33 meters was needed to obtain an energy equivalent to a 30-meter free fall. The primary treatment consisted of 30 drops at impact points spaced 50 feet center to center. Secondary treatment was 30 drops at locations between the primary drop points. Tertiary treatment was 15 drops at points splitting the secondary locations. Finally, there was an ironing phase of 2 drops from a height of 30 feet at edge-to-edge impact points. The photograph shows an overview of the upstream side of the dam during the ground treatment. Drops were continued at each location until a crater was in the range of 2.4 to 3.7 meters deep and had a corresponding diameter of 3.7 to 4.6 meters. At this point, the crater was backfilled with dredged alluvium and the drop sequence was continued. A minimum thickness of soil or backfill of 1 meter was required above the water table throughout. Very detailed analyses of the post-treatment penetration resistance values were made, and it was confirmed that the needed improvement had been obtained. Among the interesting findings was that the post-treatment Becker penetration test N-value profile was sensitive to the location of the test relative to drop weight impact points. This may be seen from the differences in the penetration resistance versus depth curves for the different test locations. The figure shows also that the level of improvement decreases with depth, as is characteristic for deep dynamic compaction. Additional evidence of the densification was provided by increases in the shear wave velocity, which averaged 280 meters per second above a depth of 12 meters and 52 meters per second between 12 and 17 meters depth. The downstream remediation was done differently. Additional investigations had provided more detail on the subsoil conditions in the redeposited dredged alluvium. Although gravel, cobbles, and some boulders were found throughout, there is an overall increase in fines content with depth. The upper 15 to 20 feet is mainly coarse sand to cobbles. The underlying 25-foot thick zone is composed of irregular layers of silty sand interspersed with sand and fine gravel with cobbles. The silty sand controls the remediation process in this zone. The bottom 10 to 20 foot thick zone is more fine-grained, containing an average of 30% low plasticity to non-plastic fines. Although deep dynamic compaction had been intended originally for downstream remediation, it was not selected for 3 reasons. First, the high groundwater level would have required dewatering. Secondly, the treatment depth by deep dynamic compaction is limited. And third, the proximity to a road raised the concern that the cratering caused by the deep dynamic compaction impacts could project gravel into the roadway traffic. In light of these concerns, and owing to the relative lack of experience in the densification of coarse gravel and cobbles, as well as uncertainties about the best method for densification of the finer material, a test program was done in 1992. The ground improvement methods studied were rotary displacement stone columns, vibropipe drain stone columns, vibrorod compaction, bottom feed stone columns, and vibrorod vibropipe stone columns. The results of the test program showed that construction through the downstream shell of the embankment was difficult. Only the vibropipe method for construction of small diameter mini columns was able to reach the required depth of treatment. However, all methods were constructible to the desired treatment depths in the zone downstream of the toe. Both vibratory probe and rotary methods for construction of large diameter stone columns by the bottom feed method produced the required density in the bottom 20 feet of fine-grained material. It was necessary, however, to use water jetting to reach the required depth. Rounded 1-inch stone was the best backfill because it was less likely to bridge in the feed tube or fracture during compaction in comparison to angular stone. The final design incorporated a 200-foot wide zone densified using bottom feed stone columns. A 20-foot wide strip of small diameter gravel drain columns was installed adjacent to the densified zone on the upstream side, and an 8-foot wide strip of drains was installed on the downstream side. The results of dynamic deformation analyses indicated the need for a block that was 900 feet long by 200 feet wide and extending to bedrock 75 feet below the original ground surface. The drainage zones were incorporated into the design because the soil both upstream and downstream of the stability block would still be susceptible to liquefaction. The drainage zones are intended to prevent migration of excess pore pressure from the liquefied material into the densified stability block. To minimize the required block width, the results of the analyses showed that the block should be as far upstream under the dam shell as possible. Temporary excavation of the upstream slope to a maximum safe inclination of 1 vertical to 1.5 horizontal was done for this purpose. This enabled construction of the large diameter stone columns from the original ground surface elevation, whereas the upstream drainage zone was installed through approximately 35 feet of embankment. Construction was done during the period from August 1993 to August 1994. The photo shows an overview during construction. The rigs in the foreground are installing columns. The one further upslope is installing gravel column drains. This photo shows a closer view of the stone column construction. Owing to the need for jetting the vibroprobes to the required depths, it was necessary to provide extensive drainage and sedimentation ponds for the removal of water and collection of sediment flushed from the holes. A gravel drainage blanket was placed over the full treated area. Becker penetration tests, standard penetration tests, and shear wave velocity measurements were used for QA/QC and the assessment of post-treatment properties. For purposes of control and evaluation, the total area of improvement was divided into 18 treatment areas, each 100 feet by 100 feet in plan as shown in the diagram. The stone columns were spaced 9 feet center to center in a triangular pattern. They averaged 4.5 feet in diameter and contained an average of 1 ton of gravel per foot of column. The columns were termed bottom feed stone columns wet replacement method because of the need for water to jet through the upper coarse zone and to aid in replacement of the fine material in the lower zone. 2,900 columns were installed. The acceptance criteria were based on the results of Becker penetration tests correlated to SPT blow counts. Becker penetration test resistance was measured at 1-foot depth intervals in holes located at the centroids of the stone column pattern. The improvement was considered acceptable if the average from at least 3 Becker penetration test values was greater than 18 blows per foot in the bottom third of the treatment depth and greater than 25 blows per foot in the upper third. Occasional values less than these limits were accepted, provided they were well distributed and less than 10% of the total. The results of the shear wave velocity measurements also provided evidence that the ground had been improved. This project represents the first known large-scale application of stone columns for improvement of loose soils containing large amounts of gravel and cobbles. The ground improvement done to improve the seismic safety of the Mormon Island Dam is notable in several ways. The results of dynamic deformation analyses played a key role in the selection, location, and evaluation of the treatment methods. The extensive field test program associated with the downstream remediation was essential for determination of suitable construction methods and validation of the improvement that was obtainable. Deep dynamic compaction was used successfully at an existing structure. The Becker penetration test, although not without some uncertainties concerning such issues as friction influences on the measured values and the generality of correlations with the SPT, was shown to be an effective method for site investigation and improvement evaluation in soils having a large gravel and cobble content. Stone columns can effectively improve soil types ranging from quite coarse, gravel and cobbles, to soils containing appreciable fines contents. The provision of drainage zones at the boundaries of densified blocks offers protection from post-earthquake strength reduction in the densified block caused by inward migration of excess pore water pressure. The 3 case histories that I have described provide excellent illustration of how ground improvement can be used to improve dam safety. Deep densification, different types of grouting, and admixtures installed by deep mixing and jet grouting offer a range of treatment methods. New analysis and design methods make it possible to evaluate alternatives and to select methods with more confidence. The case histories have shown that on many projects, more than one method of ground treatment can be used to accomplish the needed improvement. Experience shows also that there is unlikely to be any single and unique solution to dam seepage and instability problems. Rather, there are choices, and developing an optimal solution requires consideration of many factors, many of which may be unique to the project. For example, in a current case, it has been determined that the foundation soil beneath an existing Corps of Engineers dam in the southeastern United States is potentially liquefiable. At a concept meeting, engineers from the Corps and their consultants proposed 26 different ways to solve the problem. After consideration of the pros and cons of each of these methods, the most promising 3 have been selected for more detailed study. Dams with improved soil zones have performed well under static load conditions. Few, if any, existing dams where ground improvement has been used have been subjected to strong earthquake shaking. However, there is a growing database of other sites improved for other purposes that have been through earthquakes in California and Japan. Analysis of the performance of these projects has shown that the ground improvement has been very effective in preventing or limiting liquefaction and excessive deformations. There is no reason to expect that dams would do otherwise.